Today we're going to be talking about finding the area of polar curves. But before we get to the calculus, I want to remind you of some of the classical curves that you can see in polar. First is our rose, where we have a general formula A cosine n theta or sine theta. The n gives us the number of petals. So if n is even, then you have twice as many petals as whatever n is, and then if n is odd, that's how many petals you will see. Okay. Lemniscate, we'll see sometimes, not a whole lot. Limesons and cardioids are similar, just in the structure. If the A and the B are the same, we consider that a cardioid, or kind of a heart-shaped graphs. And then, of course, circles and lines. So circles can either be just centered at the origin out some radius to look like that, or r equals sine theta or cosine theta. There can be a coefficient here. For curves, if it's a cosine, then it's going to be symmetric to the x-axis. If it's a sine curve, it'll be symmetric to the y-axis. So let's look at how we find area. When we first started talking about definite integrals and finding areas, we introduced you to the idea of a Riemann sum and using rectangles of infinitely small width to represent the area. We have a similar idea in polar, except for instead of the rectangles being vertical, we actually don't have rectangles. We're looking at a sector. Okay, I'll kind of make this a little bit bigger just to kind of exaggerate it. Okay. But our cross sections are going to be sectors as you move around the curve. We want these to be infinitely small. So my angle is going to get really, really small, which is going to give me a d theta rather than a dx. So the formulas, and this comes from the area of a sector, is going to be the integral from theta 1 to theta 2 of 1/2 the function in terms of theta squared. Or a little bit simpler, from theta 1 to theta 2 of 1/2 r squared, or pretty commonly, we'll just pull that 1/2 out, and it's 1/2 from theta 1, theta 2 of r squared. This is a formula that you definitely want to have memorized. Okay. In our first example, we're just going to simply find the area of the region bounded by the graph of r equals sine theta from 0 to pi. Okay. Well, sine theta is a circle symmetric to the y-axis. So the graph would look like that. This would be 1 up here. And we're finding the area from 0 to pi. So we'll set up our integral. 1/2 the integral. Theta 1 is 0, theta 2 is pi, of our function sine theta squared, d theta. Okay, now for right now, we can just type this into the calculator and we get 0.785. Okay, well, let's think about this geometrically. If I just wanted to find the area of this circle, this has a radius of 1/2. So the area would be pi r squared, where pi is 1/2, or pi over 4. Well, if you type pi over 4 into your calculator, that's exactly what you get here. Okay, our next example, prove that the area of a circle with radius a is pi a squared. Okay, so back to our circle idea. Circle of radius a just goes like that. Okay, so if I use my rule we just talked about, 1/2, we're going to go from 0 all the way around the circle to 2 pi. And then it's going to be the function is just a, and then square that for the formula. So 1/2 r squared, my r in this case is a. Okay, well, if I integrate this, a is just a constant, so a squared is just a constant. So we're going to have a squared times theta, because that's our variable. We'll evaluate this from 0 to 2 pi. Okay, and then if I plug in 0, we get 0. So ultimately what we end up with is, so the 1/2 and 2 cancel, and we're left with pi a squared. You might get some classic curves, but you might just get some random curves that they come up with, which actually tends to be more common. So we're going to go ahead and try this one. So we're finding the area of this curve on this interval. 1/2 the integral from 0 to pi of r squared. Okay, again, just use your calculator. When you type it in, you can leave it in just function mode in x, and you'll get the correct thing. But make sure you are in radians. Okay, in our next example, we're looking at a classic curve called a rose. Okay, this has a 2 here, which is an even number, so we have twice as many petals. Okay, so there's going to be 4 petals here. Okay. Next, we're going to graph both the rectangular and polar graph of y equals 2 sine x, or for polar, r equals 2 sine theta. Okay, so thinking back to our trig days, the period of this is going to be 2 pi divided by 2, so pi. Okay, that's going to give me 1 cycle. I'm going to go ahead and put pi here. Makes that pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, 3 pi over 2, and 2 pi. We're going to go up to 1 and down to -1. This is a graph of sine. It's going to complete 1 cycle in pi. Okay, and I'm doing 2 cycles because I want to see the 4 petals. Okay. Next, we want to look at the polar curve. So each of these maximums, that's going to be our petals. So I'm just going to draw myself a little circle here. And my pi over 4, 3 pi over 4, and so on, we have our petals. Okay. Not the prettiest one in the world, but there you go. One thing that I forgot to mention earlier is when we are integrating, when we're using the area formula, the values that you're integrating must be non-negative, meaning they can be 0 or positive, but not negative values. So if I look at this graph, the values that are non-negative are here and here. So between 0 and pi over 2, and from pi to 3 pi over 2. Okay, the reason this is important to identify is if I just went from 0 to 2 pi like I did on the previous couple of problems, you're including areas that are positive and negative, positive, negative. So what's going to end up happening is they would end up canceling each other out. So, no, we cannot include negative numbers. So what we're going to do is find the area of 1 petal and find the rest of it. So for 1 petal, we're just going to find from 0 to 2 pi using our area formula, or pi over 2, of my r, which is sine 2 theta squared, d theta, so 1/2 r squared again. Using our calculator, we get 0.392. Well, if we find the area of 1 petal, we can now find the area of the entire rose by multiplying that by 4. Okay, we could have done this right from the beginning by just taking this integral that we did for 1 petal and just multiplying it by 4. Now we're going to look at the area bounded by 2 polar curves. Okay, so from the origin, if I were to draw a cross section out here, okay, I've got an outside and an inside. So what we're going to do, and this is fairly straightforward, we're going to find the area of the outside function and then subtract the area of this inside one. We're given two equations, 2 plus 2 sine theta, which is a cardioid, and 3 plus sine theta, which is a limacon. But if we're not sure, we see here at pi, because this would be 0 pi over 2 pi, at pi, if I plug pi into this one, we're going to get 2 plus 0, so we'd get 2. If we plug pi into this one, we'd have 3 plus 1, sorry, 3 plus 0, which would give me 3. So this inside one here is the 2 plus 2 sine theta, and the outside one is the 3 plus sine theta, because it crosses at 3, this one crosses at 2. So when we set up our integral, we're going to go from pi over 2 to pi. Okay, and we'll do the outside minus the inside. So I'm going to do 3 plus sine theta squared. Then I'm going to subtract the inside one. Okay, so we're going from pi over 2 to pi for both of them, and then it's just 1/2 r squared minus 1/2 r squared, which gives us 5.498. Okay, now we can condense this all to one integral, since my limits of integration are the same. So you could think about this as 1/2 from theta 1 to theta 2 of the outside squared minus the inside squared. So you can do it all in one integral, doing it like that, where the big R is the outside and little r is the inside. Okay, so we've got the graphs of our cardioid, 4 plus 4 cosine theta, so that's going to be this guy, and a simple circle, r equals 6, which is this one. So first we're going to find the intersections of the two curves. So to do that, we'll just set the equations equal. And solve for theta. Okay, so we're looking for where the x values are 1/2 on the unit circle, which is going to be at theta equals pi over 3, and either 5 pi over 3 or negative pi over 3. Either of those are acceptable. So to show that on my curve, there's our intersection. There's our intersection. So this is pi over 3. This is negative pi over 3. Okay, so we're going to do 3 different integrals. We're going to first do inside the cardioid, outside the circle, inside the circle, outside the cardioid, and then inside both the cardioid and the circle. Okay, so first, for inside the cardioid, but outside the circle, we are talking about this area here. Okay, I'm going to take advantage of this symmetry, and I can go from negative pi over 3 to pi over 3, or I can double going from 0 to pi over 3. So we'll have 1/2 the integral, well, 2 times the integral from 0 to pi over 3, or go from negative pi over 3 to pi over 3, that's fine. Okay, and then it's going to be my cross sections, and if it helps to do a sample, is going to be outside minus inside. So the outside is going to be the cardioid, the inside is going to be the circle. So we'll have 4 plus 4 cosine theta squared minus the inside function squared, which is just 6. Okay, the next one is inside the circle but outside the cardioid. So now we're looking at all of this area. Okay, so if I were to do a cross section here, the outside is the circle, the inside is the cardioid, and we're going to go from pi over 3, either from pi over 3 all the way to 5 pi over 3, or just double going from pi over 3 to pi. Okay, so I've set that up. 2 times the integral from pi over 3 to pi, since I'm just going to do half and then double it. And the outside is the circle 6 minus the inside cardioid squared, which gives us 56.309. Okay, the last area we want is combined. We want this inside section here. Okay, well, if we look at it, if I go from the origin in this section, from here to here, the only equation that's involved is the circle. And then if I go above pi over 3 or below negative pi over 3, it's just the cardioid. So I'm actually going to do this in 2 integrals. I'm going to again use the symmetry, so I'm going to find this area and I'm going to find this area. This one is just going to involve the circle from 0 to pi over 3. This one's just going to involve the cardioid from pi over 3 to pi. So we have doubling because we're just looking at the top half, but we want to double it to get both halves. The circle from 0 to pi over 3, and then the cardioid from pi over 3 to 4. Which gives us 56.788. Our last problem is going to be from the 2018 BC exam. It was number 5, which means it was a no calculator problem. So they provide the graphs for you, which is pretty typical, of r equals 4 and r equals 3 plus 2 cosine theta. So we see we've got the circle, r equals 4, and then this one's over here. The two curves intersect at pi over 3 and 5 pi over 3, so that's helpful. Then it says let R be the shaded region that they've got shaded here, inside the circle but outside the limison, as shown in the figure above. Write an expression involving an integral to find the area for R. So notice we don't have to evaluate, we just need to write the integral. Okay, so I'm going to go from here to here, which we're told is pi over 3 to 5 pi over 3. And then our cross sections, it's outside minus inside. So it's going to be the 4, the circle squared, minus 3 plus 2 cosine theta squared. Okay, and that's all we have to do. Okay. Next, we're going to go back to an old favorite, finding the slope of a tangent line. So in polar, we know that the slope of a tangent line is dy dx. So in polar, we need dy d theta and dx d theta. So I'm going to start by finding an expression for x and y. Okay, so recall x is always r cosine theta. So for our problem, r is 3 plus 2 cosine theta. And then I need the derivative. So dx d theta, we're going to need to do the product rule. So the derivative of this will be negative 2 sine theta, cosine theta. Derivative of cosine is negative sine theta. 3 plus 2 cosine theta. Okay, and then we'll repeat this for y. Y is always going to be our sine theta. And then find that derivative. Okay, so doing another product rule will give me this equation. Okay, for the slope at pi over 2, we're finding dy dx at pi over 2, which is going to be dy d theta over dx d theta, evaluated at pi over 2. Okay, so I'm going to take this whole thing, plugging in pi over 2 for theta, divided by this whole thing, divided by, or plugged in for pi over 2. Okay, and I realized I forgot the 2 there, so make sure to copy that down. So put the dy d theta over dx d theta, plugged it in at pi over 2. Now you could leave it like this, which you probably should, but we'll go ahead and evaluate anyway. Remember, sine of pi over 2 is 1, cosine of pi over 2 is 0. So in the numerator, this is going to go away, and we're going to have 1 times a negative 2. In the denominator, this will be 0. This is going to be 1 times 3 plus 0. So we get a negative 3, which gives us 2/3. Okay, and the third part of this AP question says a particle moves along the portion of the curve r equals 3 plus 2 cosine theta for 0 to 2 pi. The particle moves in such a way that the distance between the particle and the origin increases at a rate of 3 units per second. Find the rate at which the angle theta changes with respect to time at the instant when the position of the particle corresponds to theta equals pi over 3 and indicate units of measure. All right, so looking at this problem, it says the distance is increasing at a rate of 3 units per second. Well, the distance from the origin is just the r value. So that's really saying dr dt is a positive 3. Okay, well, we have our equation r equals 3 plus 2 cosine theta. And I'm going to take this derivative with respect to time. So all of a sudden, this is a related rates problem. So if we take this derivative with respect to time, we're going to have dr d theta, or dr dt. 3 goes to 0. We'll have a negative 2 sine theta times d theta dt. What we're solving for is the rate at which angle theta changes, which is this piece here. So we'll replace 3 here. We want theta to be pi over 3. And then solve. So the d theta dt would be 3 divided by negative 2 sine pi over 3, which is just fine. Sine of pi over 3 is root 3 over 2. So this would end up being negative 3 over root 3, which would then rationalize to just negative root 3. The last piece was indicate units of measure. Well, if we think about what theta is measured in and what t is measured in, theta is going to be radians. T, we're told, is seconds. Okay, so that's how we find the area of polar curves, and then a little bit of review of other stuff we can do in polar.